Hi, this is part 2 of a static equilibrium problem, taking a look at an adventurous bear trying to get a picnic basket that's being suspended at the end of a long beam. So in part 1, we took a look to see if a bear was standing 1.2 meters away from the hinge that's connected to that beam, is the bear going to be okay at that point? And we said that yes, the tension in our cable could be up to 800 newtons. It's only 431 newtons right now, so the bear's going to be fine. But for the bear to get the picnic basket, it needs to go the entire 4-meter distance, which means we need to make sure we don't have a maximum distance that would kick in before we exceed the maximum tension in our cable. So going back to the sum of the torque equation that we worked with, if the sum of our torques in our z-axis equals 0, our counterclockwise torque needs to equal the sum of all of our clockwise torques. So our counterclockwise torque is from the tension in the cable if we calculate our center of rotation being from around the hinge, which had forces that we didn't know the size of in part 1. So the torque calculated around this end of the beam is going to be equal to the length of the beam times the tension in the cable times the sine of the angle between the cable and the beam. Now in the clockwise direction, the bear produces a torque equal to the location of the bear right now times the normal force the bear produces on the beam, which is just the same size as the weight of the bear because the beam happens to be horizontal. It would also be the torque from the weight of the beam itself, which occurs at the center of mass of the beam, half the length of the beam, times the weight of the beam, and then the torque that we get from the basket on the end. Now the basket is producing a tension from how it's attached to the beam, so that distance is the length of the beam. The normal force would be the weight of the basket, essentially, again, horizontal 90-degree angles, so that would be 60 newtons. So to find our maximum distance, we'll let our tension be our maximum tension of 800 newtons. So to solve for my distance x, the first thing I'm going to do is subtract the torque created by the basket and the torque created by the weight of the beam from both sides. So my distance x max times the weight of the bear would be the length of the beam. Hey, it shows up in all three terms. So I can distribute out the length of the beam. So then that would be multiplied by the tension in our wire at its maximum, 800 newtons, times the sine of the 50-degree angle that cable makes with the beam, minus half the weight of the beam, or 120 newtons, minus the 60 newton force created by that basket. So my maximum distance then would take that torque and divide by the weight of the bear. So if we calculate things out, we have our tension times the sine of theta minus 120 newtons minus 60 newtons. We end up dividing by 500 newtons and we get a value of our force term over our force term of a little bit around 0.87 multiplied by our 4-meter distance. That means the bear gets 3.46 meters away from the hinge. So within almost arm's distance of the basket. But again, if you watched a lot of 70s early morning Saturday cartoons, you know what happens. The cable snaps, the basket goes through the bear's arms, and the other bears kind of laugh at him. Thanks for watching part 2.